Okay, so for those of you who weren't able to hear me because of our little internet issue, so there's two kinds of forces: the forces that touch objects and the forces that don't touch objects but are still interacting with the force. The first force is called the applied force, and that is the one that we've been talking about the whole time. When we have been saying force equals mass times acceleration, we've been talking about the applied force, and we write it like this: F applied subscript. And that's the force that we just do, that's the push or the pull, like we've been talking about the whole time. The push or pull on an object, and if I'm pushing this wood, if the bat's hitting the ball, this lady's pushing the table, this guy's pulling down the barbells. So it's an applied force put on an object. That's applied force. Another kind of force is the normal force, and we write that with force and a small capital N, the normal force. This one's a little tricky. It has to do with two objects in contact with each other. So a book on top of a table. And so the normal force is the force acting on the object by the table. And the normal force for the table is the object acting its force upon it. So the normal force is usually perpendicular to the surface that these forces are happening on. Another kind of force is frictional force. We do that with a capital F, little lowercase f, and we've talked about friction before. So friction, we've got these surfaces, and one object is moving along another object. But in reality, these objects are not perfectly smooth. They have little imperfections in them, and so do the objects rubbing across the top. And so when they get together, they make this kind of resistance to move, which is friction. So friction usually acts in the direction opposite the applied force is acting on. Okay. And then there's tension force, like the pendulum lab we've done, force with tension. So anything that has a rope or a string and something's hanging from it, or like these guys are pulling the rope, that rope has a tension force. So it could be string, rope, cable, wire, whatever. So that's a tension force. The spring force is a little complicated, so that's anything that can stretch or squish further together. So a couple examples. One could be a spring, like if we have the slinky all coiled up normally and we're not doing anything with it, it's at rest. Then we refer to that as being in equilibrium. And if we stretched the slinky out, then it would have this stretching constant, this force of stretch. And the spring force would be the desire for it to go back down into its normal equilibrium spot. So Hooke's law is telling us that the force of spring, the spring force, is the force that requires to take it out of stretch, to take it out of its normal equilibrium spot. And Hooke's law says that most springs, the spring wants to return to equilibrium, and so that's what the magnitude of the force is, to return to its compression equilibrium status. This could be true for like a rubber band too. A rubber band at equilibrium is just sitting there, but when we stretch the rubber band all out, it's going to have this force to stretch it out. It takes force to make it go that way. And then it wants to return back to its rest state. Okay, so please watch this video. I gave you the link. But basically he's talking about a force diagram. So we have to make force diagrams, and there's rules to making the force diagrams. So you need to label all the forces and use arrows, and the size of the arrow or length of the arrow makes a difference. So anything not moving, everything's equal. That means it's not moving, it's at rest. But if we have an object and we see that one arrow is way longer than another arrow, then we know it's moving in the direction of the unbalanced force. So when we're actually doing all these problems of F equals ma, we're really finding out what the net force is, which is the sum of all the forces. So it'll be like the force normal plus the force of gravity plus the force of applied, and that will equal the mass times acceleration, and that will give us information about all the forces acting on that object. So for example, in situation A, we have 4 forces acting on this object. And just so we are all clear, when something is moving to the right, we make that be in the positive direction. If it's moving up, that's considered a positive direction. Left is a negative direction, and down is a negative direction. So when we're looking at the sum of all these forces, we got to add all of these up. So we have the force normal, which is the up one, is 3 newtons. We have the force of gravity, which is a negative 3 newtons because it's going down. We have the applied force, which is 5 newtons. And we have the force of friction, which is negative 5 newtons because of our directions up here. So the sum of all these forces for part A is, the net forces are 3 minus 3 plus 5 minus 5. And if we look at that, that equals 0. And since it's at 0, this object is at rest. And all the arrows are equally drawn, which also means it's at rest. So let's look at situation B. So now we have the sum of these forces is the normal force plus the force of friction plus the force of gravity. But gravity and friction are going down, so those are going to be negative direction. So now we have 3 newtons for the force of normal minus the force of friction minus the force of gravity. So that gives us a total of negative 5 newtons, which tells us that the object is moving in the negative direction, the left, to the left. And we know this is moving because there's no balanced force. It doesn't equal 0 over here. So it's moving to the left. Situation C, we can see that we're going up 20 and down 20, so that equals 0. So this is at rest. And then D, the sum of the forces is 40 newtons minus 25 newtons for the down gravity. And that gives us a total of 15 newtons, which means this object is moving upward. So maybe it's like a little ball being thrown up or something to that effect, but it's going upward. So that's how we draw our free body diagrams, and we'll talk more about that on Monday. All right, thanks.